Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on analytical dynamics or classical mechanics. Chapter Lagrangian dynamics, in which I will describe about generalized velocity and generalized component of effective force. Now, I will give you the concept of generalized velocity. Let q1, q2, q3, qn be n generalized coordinates of a dynamical system. Let vector r mu be the position vector of muth particle of mass mu of the system at any time t, so that r mu vector is a known function of q1, q2, qn and time t. Therefore, we write r mu vector is a function of q1, q2, q3, qn t, implies that dr mu vector by dt, differentiating both sides with respect to t. Firstly, we differentiate partially r mu vector with respect to q1 dq1 by dt plus we differentiate partially r mu with respect to q2 dq2 by dt plus plus we differentiate vector r mu with respect to qn dqn by dt plus, now we differentiate r mu vector with respect to t dt by dt. Here we see that 1 1, here 2 2, here n n, so we may write this in sigma form. Sigma partial derivative of r mu with respect to del q I dq I by dt, I equal to 1 to n, and this term partial derivative of r mu vector with respect to t dt by dt 1. We may write this as dr mu by dt as r mu vector dot. Dot means derivative with respect to t, and right side will be sigma I equal to 1 to n partial derivative of r mu vector with respect to qi, and here we write qi dot dq by dt means qi dot plus partial derivative of r mu vector with respect to t. Here qi dot is called the generalized velocity. Or qi dot is the component of generalized velocity. Now, I will give you the concept of generalized components of effective force. Let q1, q2, qn be n generalized coordinates of a dynamical system. Let r mu vector be the position vector of muth particle of mass m mu of the system at any time t, so that vector r mu is a known function of q1 q2 qn and time t. Therefore r mu vector is the function of q1 q2 qn and t. This is number 1. If delta r mu vector is the virtual displacement of the dynamical system, then delta r mu equal to, firstly we differentiate partially r mu vector with respect to q1 and delta q1 plus, now we differentiate r mu vector with respect to q2 partially. The partial derivative of r mu vector with respect to q2 delta q2 plus partial derivative of r mu vector with respect to qn delta qn. Since for virtual displacement delta t equal to 0, so we have not differentiated r mu vector with respect to t, because here the term delta t appears and that delta t equal to 0. We may write this as delta r mu vector equal to sigma I equal to 1 to n, here 1 1, here 2 2, so we write here sigma partial derivative of r mu vector with respect to qi delta qi. Let this is number 2. Let T be the kinetic energy of the given dynamical system. Therefore T equal to sigma half mass m mu r mu dot square. Here mu means mu denotes the muth particle and also the sigma denotes sum of kinetic energy of all particles. Let this is number 3. Implies that partial derivative of t with respect to qi dot sigma mu half a mu. Firstly we differentiate this with respect to r mu dot, means 2 r mu dot, then del r mu dot by del qi dot, partial derivative of r mu dot with respect to qi dot. This equal to 2 to cancel sigma mu a mu r mu dot, partial derivative of r mu dot by del qi dot. This is number 4. Differentiating 1 with respect to t, we get dr mu vector by dt equal to partial derivative of r mu vector with respect to q1 and dq1 by dt plus partial derivative of r mu vector with respect to q2 dq2 by dt plus plus partial derivative of r mu vector with respect to qn dqn by dt plus partial derivative of r mu vector with respect to t dt by dt implies that left side is r mu dot differentiation with respect to t, r mu dot is equal to partial derivative of r mu vector with respect to q1. Here dq1 by dt is q1 dot. q1 dot. Similarly, second term will be partial derivative of r mu vector with respect to q2 dot plus partial derivative of r mu vector with respect to qi dot plus partial derivative of r mu vector with respect to qn dot plus partial derivative of r mu vector with respect to t. Here dt by dt is 1, implies that differentiating this with respect to qi dot, here we have term qi dot, so partial derivative of r mu dot vector with respect to qi dot, here 1 and other will be 0. So partial derivative with respect to qi dot will be 0, 0, here 1. Partial derivative of r mu vector with respect to qi. This is number 5. Using 5 in 4, we get partial derivative of t with respect to qi dot equal to sigma mu m mu r mu dot vector, and this is will be partial derivative of r mu with respect to qi, using this in 4 here. Now differentiating 3 with respect to qi, we get partial derivative of t with respect to qi. This will be sigma mu half m mu r mu dot partial derivative of r mu dot with respect to qi. Let this is number 5, this is number 6. This is using 6 in 4, and this is number 7. This is number 8. Since r mu double dot be the acceleration of muth particle and a mu r mu double dot be the effective force, mass into acceleration, on muth particle. Let delta W be the virtual work done by the system. Therefore, delta W equal to sigma mu a mu r mu double dot, this is force, dot virtual displacement. Let this is number 9. Using 2 in 9 we get, means we put the value of this virtual displacement taking from equation 2. We get delta W equal to sigma mu a mu r mu double dot, and this is sigma I equal to 1 to n partial derivative of r mu vector with respect to qi delta qi. We may write this sigma I equal to 1 to n a mu r mu, here sigma mu double dot partial derivative of r mu with respect to qi delta qi. This will be equal to sigma I equal to 1 to n sigma mu a mu, here we may write d by dt r mu dot partial derivative of r mu vector with respect to qi minus r mu dot d by dt partial derivative of r mu vector with respect to qi. This bracket close, and here delta qi, this equal to sigma I equal to 1 to n sigma mu d by dt a mu r mu dot partial derivative of r mu with respect to Qi minus sigma mu A mu R mu dot. We exchange partial derivative and total derivative here. Del by del Qi partial derivative d by dt R mu vector. Here bracket closed. Here this bracket also closed. This bracket also closed. Delta Qi. This is equal to sigma I equal to 1 to n bracket sigma mu d by dt A mu R mu dot partial derivative of R mu vector with respect to Qi minus sigma mu A mu R mu dot partial derivative with respect to Qi. Here d R mu by dt is R mu dot bracket close delta Qi. This is number 10. We may write equation 10 here. Here we have sigma mu. We write d by dt first, then we write sigma mu here, and other term remains same. This is number 11. We put this value from 7 and this value from 8 using 7 and 8 in 11. We get virtual work done by the system equal to sigma I equal to 1 to n d by dt. This is from 7 partial derivative of t with respect to Qi dot minus this is partial derivative of t with respect to Qi in 8 multiply delta Qi. This is number 12. Since delta Qi be the component of general displacement, so this is the displacement and this is the force. Force multiplied displacement is the work done. Therefore, d by dt partial derivative of t with respect to Qi dot minus partial derivative of t with respect to Qi will be the generalized component of effective force. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.